Alright class, so this is a Lewis structure video, and basically I'm just going to walk through the strategies behind drawing some Lewis structures and then also talk about calculating formal charges and also indicating the relative polarity for each of the different bonds that we're seeing in there, the covalent bonds. So let's go ahead and get started. The first Lewis structure that I'm asked to draw here is this CH3CH2OH. So this is ethanol. And you'll notice that it's written out in sort of maybe a different manner than we might typically see. All the carbons are not grouped together, all of the hydrogens are not grouped together. And the reason that it's written out like this is really to help us draw the Lewis structure. It's really to show us what the connectivity of the molecule is. So when you see something like this, it's really giving you hints as to how you should think about drawing the structure. So the first thing, obviously, that we always want to do is calculate the number of valence electrons. So I calculate 20 valence electrons. And of course, I always say you have to do this because you always have to check your structure to the number of valence electrons. All of the valence electrons need to be accounted for in your Lewis dot structure. So if you're not doing this, really shame on you. You really need to be doing that as another check for your Lewis structure. Okay, enough of that. So now I can start drawing sort of the skeleton structure of what I think this thing should look like. And again, the reason that this is written out this way is really to help us with that drawing. So I'm going to start by writing CH3. So I've got my CH3, so I see CH3 right here. I'm going to draw out sort of a CH3 group just like that. That's going to be bonded to this next carbon. And I've got H2, so off of that I'm going to put 2 hydrogens. And then I've got OH at the end, so I'll put an O, and then I will put an H. So this would be the way that I would draw this picture, really based off of what I'm being told here. Now I've got to fill in my valence electrons. I want to fulfill the octet rule for oxygen, so put 2 lone pairs of electrons here. And then I can count, I can double check, do I have all of my valence electrons accounted for? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 valence electrons. So that is a good picture. The next thing I want to do is calculate the formal charges. And the formal charges, the way that we calculate that's going to be the number of valence electrons minus the number of lone pair electrons, not the number of lone pairs, the number of lone pair electrons. So if I've got 2 lone pairs, that would be 4 lone pair electrons. And then minus the number of bonds. And you, depending on what your textbook says or other sources, you're going to see this number of bonds written differently. You're going to see it written as 1/2 the number of electrons that are in bonds, which is really just another way to say the number of bonds. So I like simplifying this to say the number of bonds. So this calculation here will tell us what the formal charge is. So let's do this for hydrogen, for instance. Hydrogen has 1 valence electron, right? So you're just using off my periodic table, 1 valence electron minus 0 lone pair electrons. So all of these hydrogens, they're all in sort of the same environment with 1 bond to them. Minus 1 bond equals 0. So all of these hydrogens will have a formal charge of 0. For carbon, that's going to be 4 minus 0 minus 4. So 4 valence electrons for carbon, 0 lone pair electrons, 4 bonds to each one of my carbons, again 0. And for oxygen, we're going to start with 6. We're going to subtract 4 for the valence electrons, 4 for the lone pair electrons, and then 2 bonds equals 0. The last thing we need to do is indicate the relative polarity. So I've got 2 polar bonds in this molecule here. Remember that CH bonds are non-polar, so that is this one sort of non-polar type bond that we really do need to remember. So these CH bonds and CC bond obviously will be non-polar as well. So these will all be non-polar, but then the CO bond and OH bond, those will both be polarized because the oxygen is more electronegative than hydrogen or carbon. So let's do the next one. So the next one is ClO4 with a minus charge. So ClO4 minus. So the first thing again I want to do is calculate the valence electrons, 32 valence electrons. And in this case, when I see something like ClO4, in my mind, immediately I'm going to be thinking that the chlorine is in the middle and that the 4 oxygens are around the outside. This one's a little bit strange, right? Because normally when we see chlorine, we think to ourselves, well, chlorine wants to only have 1 bond and 6 electrons around it, right? That's how it gets to a formal charge of 0. We always want to make our formal charges equal to 0 if possible. So in this case, this is a little different, but we're going to go with it and sort of see what we come up with. So I'm going to put the chlorine in the middle, and then I'm going to first put the 4 oxygen atoms just arranged around the central chlorine, okay, just like this. Now I see that this overall thing has a -1 charge. So the overall compound, right, so this is just a bracket here, I'm just leaving off the rest of the bracket, but the overall compound has a -1 charge. And so in my mind, what I'm thinking is that the number of the formal charges are going to have to add up to -1. And really what we want to do is we want to have one atom have a -1 formal charge, and then all the other atoms have a neutral formal charge. So in this case, we're going to break the octet rule. We're going to blow the octet rule out of the water. And so really we should think of the octet rule as really more of an octet suggestion. It would be good to follow the octet rule, but the formal charge rule is really more important than the octet suggestion. So here, based on my sort of experience with chemistry, what I'm going to do is I'm going to make one of these oxygen atoms have 6 lone pair electrons, so 3 lone pairs, and 1 bond. Because I know if I calculate the formal charge for this oxygen here, it's going to end up with an overall -1 charge, right? I sort of can do that in my mind. And then for all of these other oxygens, I'm going to make 2 bonds with 2 lone pairs of electrons. So this is a structure that I think is probably a good structure. The first thing I'm going to do is calculate my valence electrons, make sure that adds up, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 10, 12. That's perfect, 32 valence electrons. And let's go ahead and calculate the formal charges. So we'll call these oxygens A, so they have the similar sort of arrangement, and this oxygen B. So for oxygen A, I start with 6 minus 4 minus 2 equals 0. Oxygen B, 6 minus 6 in this case, minus 1 equals -1, so that's my -1 charge. And then chlorine, we have 2, 4, 6, 8, 10, 12, 14 electrons around that chlorine. So the octet rule here has, like I said, it's been totally blown out of the water. We've totally ignored the octet rule. But if we calculate our formal charge, 7 minus 0 minus 7 equals 0. So the fact that we have a 0 formal charge equals 0, it really should help alleviate any stress we have about breaking the octet suggestion. The fact that the formal charge is equal to 0, that's more important than the octet rule. So this scenario, right, when we're nervous about breaking the octet rule, calculate the formal charge. If the formal charge equals 0, we're minimizing our formal charges. That's going to be sort of the better way to draw these structures. Okay, let's do one more. PS3 minus. Here we're going to have 24 valence electrons. And just to reiterate how I'm doing that, phosphorus has 5 valence electrons. Sulfur has 6 valence electrons, so we add that up. That will be 23, and then since it's minus, we're going to be adding in 1 more valence electron, right? So the minus charge comes from having 1 extra electron, so we're just going to add that extra electron in. Again, if I see something like this, PS3, I'm going to put the phosphorus in the middle, and I'm going to arrange my sulfur atoms around the phosphorus, around the central phosphorus. And then I'm going to start thinking about electronegativity. I'm going to be thinking about, what's this, going to be going on with this? How do I get this overall charge of -1? And again, I know, like through my experience, that having one atom with a -1 charge, that's going to be the best way to sort of draw this structure. And I know for sulfur has the same number of valence electrons as oxygen. So if sulfur has 3 lone pairs or 6 lone pair electrons around it and 1 bond, then this sulfur here will have an overall -1 charge. And then I can fill in the rest for my other sulfur atoms. with 2 bonds and 2 lone pairs, and I know that that's going to end up giving that, the sulfur A's and sulfur B. My sulfur A is going to end up having 6 minus 4 minus 2 equals a 0 formal charge, whereas sulfur B is going to end up with the same 6 minus 1 equals minus 1 formal charge, right? So that's where the minus 1 formal charge for this whole molecule comes from. And then for the phosphorus, again, we're breaking the octet rule here, right? We've got 2, 4, 6, 8, 10 electrons around that phosphorus, but 5 minus 0 minus 5 equals 0. That formal charge equals to 0 should, again, alleviate any stress we have about that phosphorus breaking the octet rule, because the formal charge rule is really, a better rule. One last thing I do want to mention here, really we have a choice here. We could imagine taking these electrons here and making another double bond with phosphorus, having 3 double bonds, phosphorus to sulfur. All of the sulfurs would then have a neutral charge, neutral formal charge, and then the phosphorus would be the one that's left with a minus 1 formal charge. But when we're doing this, we always want to have the formal charge be on the more electronegative element. So sulfur is more electronegative than phosphorus. So if you did come up with that other drawing where we have 3 double bonds, the reason why this one is simply better is that the formal charge is residing on a more electronegative element. Just think about what electronegativity is, right? It's how much does that atom want those electrons. So putting the formal charge of a negative formal charge on a more electronegative element should sort of make sense to us. Okay, please do let me know if you have any other questions, and good luck.